the end of the lecture so you can keep me company while I convert it. All right. Okay. So what we're going to cover today is voltage references. And I want to just go through a few fundamental things to begin with. This is chapter 23. First simple voltage reference is just a voltage divider where you have two resistors. And so here would be your, say, VDD and ground. And this is your Vref. And you might ask, if you're asked, okay, well, what are the virtues of this topology? And you get Vref is equal to R2 divided by R1 plus R2 times VDD. And it turns out, what's the first thing you see if the temperature changes? So let's write it. So it'd be R2 let's say 20 times T minus T naught. So what was the equation? Times TCR plus 1. And we do that for the other ones, R20, T minus T0, TCR plus 1, R plus R10, same thing. And what do you notice with regard to the temperature? Yeah, it goes away, and so it's independent of temperature. We covered this in like chapter 3 or 4, but what's the drawback? What are the two drawbacks of this divider? Well, no, more fundamentally, you want a voltage reference to be independent of, yeah, VDD. So it's not a voltage reference that's going to stay independent of VDD. So what's another problem here more subtle than that? Well, it depends on the application. You could have smaller, I mean, yeah, but the resistive layout, but you could have a special process step. What? No. Well, assuming most of the time when you have a reference voltage, you don't load it. It goes into like a buffer or something. Well, more fundamentally, it's the voltage coefficient. So if you recall, like if these are made with N-well, and you have your N-well sitting here, and each side is N-well's grounded. If you raise this potential up, the depletion region grows and your resistance changes, all right? So that forces you to use like poly resistors or whatever, so there's limitations there. Sensitivity to VDD is another issue. Another example is of a voltage reference is a resistive MOSFET divider or a MOSFET divider. And let's actually do the resistor MOSFET divider first. And I'm going to go through these as a background just so you know why we've spent time studying like self-bias references and all that stuff. So here's your VDD, and I want you to be able to do the math on this derivation I'm about to go through. So you gate drain connect, and just as a sanity check, you call this Vref. If you make the device really wide, what is the reference voltage going to be? No, think about it. If you have a wide device and you trickle current through a wide device, what's the VGS? Does everybody understand Vref is VGS here? Which is equal to 2ID over beta sub n plus V threshold. So if you make the device wide, what happens to beta sub n? And so what does Vref become? It goes to the threshold voltage, right? Does everybody follow that? So they can make, but the problem with using a reference threshold voltage is that threshold voltage changes with process runs, okay? But I want to go through and derive the equations for this, and in particular, I want to find the temperature coefficient of this voltage reference, how it changes, and then look at it and see, because we need to make sure we can do the derivatives of all this stuff. And I'll come back to some other things in a moment. All right, so tell me, what's the other equation I need for ID here? So I'm going to plop that in here. And did I use beta or did I use KP? So remember, beta sub n is Kp sub n times W over L. So I get Vref is equal to the square root of 2 times VDD minus Vref all over Kp sub n times W over L plus V threshold n. And I want to solve for, R. Thank you. I want you to tell me, the way this is right here, can I get a closed form solution for Vref? Can I say Vref is equal to this? No. So what I got to do in this equation is I have to say, okay, I want to design for this Vref, or I want to design for this current, and I have to plug in the values, and then I get the Vref. More importantly is I want to design for a typical temperature behavior. All right, so what I'm going to assume to make this practical is that for the temperature dependence, is that VDD is much, much greater than Vref. So this term here is a constant. Does everybody follow that assumption? Okay, so now I'm going to do the derivatives, and we're going to go through this because we'll do this over and over again, and I want you to be able to go through the math, okay? So let's write now with that assumption that Vref is equal to the square root of 2 VDD all over R times Kp sub n times W over L plus V threshold n. Okay, so I want to find the temperature behavior, so I'm going to take the derivative of this with respect to temperature. So tell me, looking at this equation, what values are going to change with temperature? R, Kp, which is the mobility, and then the threshold voltage. Does anybody recall from chapter 9 what a typical value for a long channel threshold voltage change was? It's like a millivolt minus a millivolt per degree C. If the temperature goes up, the threshold voltage goes down. For a short channel device, it's like 0.6 millivolts. Okay. Does anybody remember how the mobility or Kp changes? Well, it's minus 1.5 divided by T was the dependence, and then here, let me show you in the equations in chapter 9, just so if you have homework in this, you can go refer to them. On page 295. So you look here and you see, okay, the 1 over Kp del T is minus 1.5 at a temperature of 300 degrees Kelvin. That's minus 5,000 parts per million. Okay, and this is how we modeled it, but we're going to care more about this. Okay, so remember that. The other thing that and remember what we do is once we have this is the temperature coefficient of the transconductance parameter. That's TC Kp, if you will. Then you have your transconductance parameter at some temperature T0, and then how it changes with temperature. So all of these are, if you look, like threshold voltage is equal to the threshold voltage at some measured temperature times 1 plus the temperature coefficient times T minus T0. The other one that we derived was back in chapter 4, and that was for the resistors, right? You know, this is kind of a little bit math, but 1 over R del T is the normalized temperature behavior. So that would be like, oh, the TempCo is 2,000 parts per million, so that means its TCR is like 0.002. And where we looked at that, or where we put those values for typical values, was right here. So like you see TCR, that for, say, the N-well, TCR1 is 2400. We won't worry about the TCR2, the second order. That's TCR1 is 1 over R del T. That's the whole point of this, me babbling. Does everybody follow that? So when you see that in our derivation we're about to do, you see 1 over r del t, you know, oh, that's 0.0024 or 2400 times 10 to the minus 6, which is what parts per million means. All right, hopefully you got that. So let's take the derivative of each side. And I'm going to rewrite this because this first time, just to be really clear, of 2 VDD times r to the minus 1 times kp sub n to the minus 1 times w over L. Does the w over L change with temperature? No. And then times or plus the change in threshold voltage change with temperature. Oh yeah, thank you. Okay, does everybody see how I did this? Okay, so now I'm going to take the derivative of each one. I know what this is. I can go back in chapter 9 and know, oh, that's change in threshold is about minus 1 millivolt per degree C. I didn't show you that, and we were just there. It was like 295. So that's where was it? It's 295. I said it, and so right there you see temperature for long channel minus 1 millivolt, short channels like minus 0.6 millivolts, and then to get the temperature coefficient you divide by the threshold voltage value, say 0.8 or whatever, 250 millivolts if it's a short channel. Okay. All right. So let's go through this now and remind me, how do I take the derivative of this? Yeah, term by term, right? So I'm going to make it easy on myself, and I'm going to write this is equal to, because I want to get 100% on my quiz here, plus 2 VDD times W over L, and then times, and then the first term is, well, wait, I take the derivative, so it's minus R to the minus 2 Kp to the minus 1. Would everybody agree with that? Okay, and then that's plus, or minus, because it's going to be minus again, minus R to the minus 1 times Kp to the minus 2. Are there any questions about that? To the 1/2, yeah. To the minus 3/2, right? Or yeah, minus 1/2, thank you, you're right. And then I gotta come down here and divide this by 2. I was so worried about the chain rule that I didn't go through that. All right, so any questions there? Oh yeah, thank you. Yeah. This is 1/2. Get rid of this. Wanted to do this very clear, and now I'm blowing it. Let me start over. And I'll do it like I'm actually doing it, not trying to teach it. How's that? So that's equal to del V threshold n del t, and then the derivative of that would be plus 1/2, and then let's leave everything in there. So that would be 2 VDD over W over L times R to the minus 1. The derivative of that times minus 1 Kp to the minus 1 to the minus 1. I know I made a mistake, so hold on. Don't get freaky on me here. And so that's with respect to temperature. Everybody agree with that? Yay. And so then I can rewrite that as del V threshold N over del T, and then move this inside, and that cancels with that and gives me a 2 down there, and then I get plus the square root of VDD over 2W over L. I gotta flip it around. Square root of 2W over L divided by VDD, and then that's times minus R to the minus 2 Kp to the minus 1 minus Kp to the minus 2 R to the minus 1 to the minus 1/2. All right, looking good? And this is again del V ref del T. But the temperature coefficient of the reference voltage is defined as 1 over V ref times del V ref del T. And so my V ref is this term here. And what that gives me, oh, you know what? I left out, what else do I need to put right here and here? And this one is del Kp del T. Yay or nay? All right, so then I can rewrite this part only, and I'm probably going to stop because we're wasting too much time on this, is 1 over R Kp times 1 over R del T. So the minus 2, there's our 2 R's, right? And then I can put the minus here too. And then minus 1 over R Kp times 1 over Kp del T. So this term here is the temperature coefficient of the resistor. This term here is the temperature coefficient of Kp we talked about just a moment ago. When you divide by the Vref and you put the for the overall temperature coefficient, what you end up getting is this term right here. And let's and so if you look at it, it tells you, okay, well, how do I design for a specific temperature behavior given my given the parameters I have? What is this term right here, V threshold times T C V threshold? What's a simple way to represent that? Yeah, del V threshold over T. That's this term right here. Does everybody see that? And then this is the stuff we had in the denom. This is what we just derived. We pulled all that out, and this was our 1 over V ref. So that's our 1 over V ref, and then all of this stuff is the thing in there. So we derived that. It was good times. All right. So, and then there's an example. I don't want to actually spend much time on this. You can read through the example on your own of the resistive MOSFET, and also the MOSFET only voltage divider. You can go through. One of the circuits that's useful is this one right here, because you can use it as a if you make the device really wide, you can use it as a threshold voltage multiplier. So if you made like R1 equal to 100K and R2 equal to 100K, then this volt, and you made this guy wide, then this voltage is what? Threshold. The current that flows through here is threshold over 100K. So then the voltage here would have to be 2 thresholds in order to get the same current. And then you can adjust the resistors to get, you know, a certain value for Vref depending on whatever the threshold voltage is. Now, let's just pause before we move on. What does the threshold voltage do if we increase temperature? It goes down. What does the resistor in general do if we increase temperature? It goes up. So if I ask what does the current do through here as temperature goes up, what's your answer? It's going to decrease, right? It's going to decrease fast because we got the resistance going up, and then we got the threshold voltage going down. Okay, so now I've got a question. The overall current decreases quickly, but how does that influence Vref? How does like the resistor values going up with increasing frequency influence Vref, and why? No? What? This'll, if, well wait, think of it real simple. If this voltage is the threshold voltage, this voltage is some multiple of the threshold, right? How does this voltage change if these two resistors values change with temperature? It doesn't, because it's a resistive divider. Okay, so if this is Vref, and the temperatures here, these go from 100K to 200K, but they both stay the same, it doesn't influence the change. It influences how much current flows through here, but it doesn't influence Vref. Yeah, so Vref ideally is only influenced by the threshold voltage. So if you look at the temperature behavior here, assuming again that this node is approximately the threshold voltage, then this node is going to go down with increasing temperature. And if a factor was 2, it'd go twice as fast as the threshold, so it'd be multiplied. Okay. All right. Are there any questions on that? Because, I mean, maybe we should go through these a bit more. But what I kind of wanted to do was go through the, let me make sure I'm covering what I said I would cover today. I want to get to self-biased reference and spend the time on the self-biased references. And I want to start out in particular and talk about the beta multiplier, because we already know that one. We already know how it operates, and I want to talk about how could we use that as a voltage reference. Okay, so let's go and let's just do it on our own, which it starts here. Tried to use the mouse button to roll down on the page. Let's just pick our basic beta multiplier, and let's see, which one did we use? We used the this one is the short channel process. Tell you what, let's go back and just look at the beta multiplier from chapter 20, just to be different from the book. And let's look at the one we derived for nano CMOS, which was this guy right here. And let's try to determine the temperature behavior of this. Okay, so let's start out by just review. Does this added amplifier influence our core beta multiplier equation describing the current? No. Okay. If the threshold voltages change with process, temperature, whatever, does that influence the temperature behavior of the circuit? No. What we end up getting is the VGS of this M1 is equal to the VGS of M2 plus the current through Iref, all right? So the fact that these voltages in here are changing or whatever isn't really that important. What I'm going to say is my reference voltage, and I could pick this one and it'll change, or I could pick this one, the V bias N, and it'll change. I'm going to start out by doing the V bias N and say I'm going to use V bias N as a reference voltage. The reason I'm going to use V bias N and not V bias P is, if you recall, V bias P changes linearly with VDD. Does anybody remember that? So VDD varies, V bias P follows it, and ideally it changes the same amount, but V bias N doesn't. So I'm asking myself, can I use V bias N as a voltage reference? Because it won't change ideally with VDD. So actually, let's do it with the older one, then we'll do it with the newer one. Let's do it with this guy first. Okay? All right. So you guys are all gurus at this now. And let's see. So what I'm going to do is I'm going to write this and you tell me if we need to draw the schematic. VGS1 equals VGS2 plus ID times R. Alright, so that's the square root of 2I over beta plus V threshold N. No? Okay. Well, let's just cut to the well, here, let me finish it, and then I'll just write down the value for I. Okay, so threshold voltages divide out, and if we solve for this, we get I is equal to, where is it? Yeah, it's 2 over R squared times Kp sub n times W over L times 1 minus, yeah, I should know that. Okay. All right, but that's not really what we want, is it? What we want is, if we recall, we want this V bias N to V ref. Does everybody recall that? So in other words, what I'm going to do is I'm going to take this guy now, and I'm going to plug it back in there. And then I'm going to say V ref is equal to, because that's VGS. Does everybody agree with that? Okay, I'm going to say V ref is equal to, plugging this back in, the square root of 4 over R squared beta squared times 1 minus 1 over root K plus V threshold N. Looking good? Or, in other words, V ref is equal to 2 over R times beta times 1 minus 1 over root K plus V threshold N. Now I'm going to simplify my life and say K is equal to 4. So then I can say that V ref is equal to 1 over R beta plus V threshold N. Looking good? Alright, so now what I want to do is I want to design this beta multiplier so that V ref doesn't change with temperature. So what I'm going to do, I'm going to take that result. I'm getting lazy there. And I'm going to take the derivative of V ref with respect to temperature, and that's the derivative of R to the minus 1 times beta to the minus 1 plus the derivative of the threshold voltage with respect to temperature. And for our long channel process, what is that? Yeah, 1 minus 1 millivolt per degree C, and I'm going to set that all equal to 0. Now keep in mind, I'm going to simulate this to see if I did it right. So when I did it wrong, you can say, wrong! Okay? Alright, so I'm going to take the derivative here, and I get minus R to the minus 2 times beta to the minus 1 times del R del T plus minus R to the minus 1 beta to the minus 2 del beta del T equals 1 millivolt per degree C. I'm going to rewrite this as 1 over R beta times 1 over R del T plus 1 over beta del T is equal to 1 millivolt. Okay, so I'm going to assume that my resistor TempCo is 2,000 parts per million. So this I'm going to replace with, so does everybody, I'm saying that like everybody follows. Is everybody following? So 1 over R del T is equal to Tc of the resistor, which is 2,000 parts per million per degree C, which is 0.002. So this is 0.002, this term right here. Okay. Then I look at the chapter 9, and I don't really have, I opened right to the right page. I don't have 1 over beta del T, but isn't that going to be the same as 1 over Kp del T? Because the Kp times W over L, Kp times the W over L's cancel. So I'm going to replace 1 over beta del beta with minus 1.5 over T. T is in Kelvin. T is in Kelvin, so if I assume that's at room temperature, T equals 300 degrees K, then this thing ends up being minus, oops, I got a sign error here. And that's minus 5,000, oh, that's right, minus 5,000 parts per million. So this term ends up being minus 0.005. They divide out because the width and the length are down here. So it's 1 over Kp W over L times the derivative of Kp times W over L del T. So they divide out. All right. Is everybody cool with that? All right, so let's go and just for the one we have in the book, can we, just looking at this and the value of R and beta, can we ever get a 0 TempCo? Because I took the derivative, I set it equal to 0. The change in the threshold voltage with temperature was minus 1 millivolt. I said, oh, I can move that over here. I took the derivative of this part, R and beta. No, well, but keep in mind, I took the K out, right? So if I play around with the K, I can probably get closer to 0. So, but let's hold on with that, hold off on that for a moment. Let's just calculate what this is. Okay, so if I look at the book, or if I rewrite the equation, and I move this back in, what I'm going to get is the temperature, or the change in Vref with temperature is equal to minus 1 over R beta times minus 0.003 minus 1 millivolt per degree C. Would everybody agree with that? So what I'm going to do is I'm going to go simulate in chapter 20 the beta multiplier. We're going to look at V bias N, and we're going to see how it changes and see if it matches. Okay, so before I move on, is everybody clear on this? Because this will be the last lecture we spend on this, and then we'll move on to band gaps and all those other things that are more practical. But this is really important stuff, actually. Okay, does everybody understand how I got this? Okay, so for table 9.1, what is R for the beta multiplier? 6.5K, right? Here, I'll show you in the book. Figure 20.15. Okay, there's my 6.5K. My beta is 10 over 2 times what? And then that's times minus 0.003, and then that's minus 1 millivolt per degree C. So let me see if I can do this quickly in my head here. Or actually, I don't want to. It's late. Let's get out the calculator and let's do 0.003 divide by 6500 divide by 5 divide by 120 E6 change sign equals, and that is 0.0007. So that is minus 0.0077. So where? Oh, yeah, thank you. So that's plus and minus 1 millivolt, which is 0.001. So let me just go ahead and see what that is. So minus 0.001 equals, so it's still slightly negative, but it'll change it roughly 200 minus 230 microvolts per degree C. Now let's find out. Any questions? Okay, so let's go to figure 2015. I guess it's 2016. And what I'm going to do is I'm going to change this DC to a dot DC, and I'm going to sweep temp from 0 to 100 in 1 volt steps. And then I'm going to change this. Let's get rid of this, and I'm going to call this VREF just to be consistent. And move this over. Okay, before I run the sim, when I plot VREF, what do you think it should look like before I take the derivative or anything? Well, I'm sweeping temperature. I haven't calculated what VREF's value is, but it should have a slight negative slope, right? Does everybody agree with that? So let's find out. Does anybody not understand why it should have a slight negative slope? The simple answer to that is because the temperature coefficient's negative. Okay, so let's hit run and go for the gusto here. And there we have it, slight negative slope. But I want to prove that my hand calculations wasn't a scene from Charlie Brown and the teacher going wah, 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 wah. So tell me how I can prove that. Yeah, take the derivative. Oh, wait a sec. Oh, I did have the temperature coefficient in there. All right. If it's not my calculation, then we'll investigate. But I got a feeling it's not that close. It's minus 77. No, it's off by the. It's off by exactly the change in threshold voltage. So this is the 77. No, I think I did the calculation right. I think that the SPICE models don't model the change in the threshold voltage with temperature. So let me go look. These are level 3. Let's go investigate help topics. Because I think I'm pretty sure that's correct. Actually, let me look real quick in chapter 23 to see if it shows, because it's way too exact to be off. That's what I'm looking in chapter 23 is if any of the first you know what? Let's do instead. Let's do a save. We'll come back to this. File, save as, and let's just call it junk. I want to investigate what's the easiest way. Get out the scissors, cut everything. Because if it's not right, then I want to know why. what was the current roughly? 20 microamps or 10 for the long channel. So that's 20U. Press G. Boom. And then let's go ahead and call this VREF. And plop that down. Hit run. Nope, that means that the model does minus 640. All right, so let me go back and look at that because I think I did it right. Oh, poop. Oh, I save it as, no, that was the previous one I saved as junk. Oh, that's right. It is .temp. All right, so, oh, was this what you were saying? Yeah. So, no, but I used a W over L of 10 over, oh no, I used 10 over 2. Let me look, because it's got to work. Minus 1 over R beta. And 6.5. Let's look. So VREF is this cancels 1 over R beta. So let me just pause and troubleshoot that. So that would be 1 over 6.5K. I've done this, it always works, so that's why I'm puzzled. 6.5K times beta, which is times 120 E6 change sign times 5 equals 1x plus 0.8 equals, so the threshold, or the output should be 1.05. Pretty close. And then we take the derivative of this, which would be the derivative. Oh wait, did I drop a fact? No, the 2 goes away. It's 1 over R, which would be the derivative of R to the minus 1 times beta to the minus 1, which would be 1 over R squared minus beta. Pull the R and the beta out. We get 1 over R down. This thing is plus the derivative minus 1 threshold. It's working. Then that would be 2,000 parts per million minus the 1.5 over 300, which if I recall is 5,000. So that gives us minus 0.003, just as a sanity check. What's that? Wait, a sign on the other page? Yeah, 5,000. What? Yeah. So it's minus 1, then I pulled that back. And so this was 0.77, that's 1 millivolt.
No, it should be negative as well. When you subtracted it over, but it was negative on the other side, and then you still brought it over as a negative. You had negative 1 over RB.
So this is minus 1 over RB, minus 1 over RB, pause. And then that's minus, so this would be positive, and then subtract that. And it's 230 microvolts per degree C. Let me take the derivative one more time. I don't know, should work. And it's off. It's closer just to what the threshold voltage is changing as. All right, let's do one more thing. Bear with me. Let's hit save. So if I come back here. Where was junk? Oh, didn't I save it? Oh. Alright, so let's do it again. What I'm going to do is I want to look at the threshold voltage and make sure that it's changing. Whoops. Yeah, I don't want to hit F9 while I've got my recorder, because that stops the recorder. Yeah, I've done that before. Students don't like that because the videos stop. And then let's plop down the current source. Let's just put a microamp there. Ground. 1U. And I'm going to make this one really wide. Actually, let's see what happens if we just do this. VREF. And then hit run. And then plot VREF. Take the derivative. Now notice VREF is slightly above the threshold voltage, so I should see minus 1 millivolt. Oops. Oh, what's that? Well, here, let's do this. Let's hit save. Then I'm going to make this 100, so that I'm even closer to the threshold voltage. What? Did it go into sub-threshold, or? Oh, it's sub-threshold. All right. I think the minus 1 millivolt's a little bit. I must have derived that in chapter 9 for. Oh wait, what does it say in table 9.1? That would be, if I'm just not remembering. Change in threshold voltage. Nope. Minus 1 millivolt. Oops, you can't see that. Minus 1 millivolt for the NMOS, and minus 1.4 millivolts for the PMOS. Let me also look in the chapter 20, because I think I derived it there as well. I don't like it when things don't work out. Where's the beta multiplier? Temperature behavior. There we go. Okay, isn't that what we just derived? Oh wait, that's for 0 TempCo. Change in VREF. That's 1 over R del R. Yeah, this is exactly what we just derived, isn't it? Except there's a 2 there. Oh, but then when this K is 4, yeah, then it divides out. That's minus 1 millivolt. Then this is where we have the factor of the K. We can mess around with stuff. I don't know. It should work perfect. It must have.
When you subtract it inside the parentheses for the 0.002 and the 0.005,
Yeah.
on the other page, is it supposed to be double negative? And you have 1 over beta here, and they just have 1 over KP.
Who's they?
Right in the equation you just showed.
Oh, okay. All right. 1 over K. What, say that again? Oh, no, it's the same, though.
They don't. Oh, the W over L cancels.
Yeah, like this. I don't know. It's the exact same thing.
Those won't add, they will subtract, though, the 0.002 and the 0.005.
Well, because the temp. Well, I'm assuming that the TempCo in there was. Oh, that would be a problem. I thought it was 2. No, it's 0.002. I don't know. I don't know. Maybe I made a calculation mistake somewhere, but this is minus 1. Well, let me just double check. Yeah. And then, I don't know. Should be perfect. And that's minus. Oops, you can't see that, can you? So this is minus 1.5 over t. And so minus 1.5 over t, that's positive 0.002. And this is minus 0.003. These cancel. Oh, wait a sec. Oh, wait, that's not the right equation. It's this one. So that would be 1 millivolt minus 1 minus. And so this would be positive. I don't know. I don't see any problems. I don't know why Spice isn't matching. Maybe I have some minor thing in there or something. I don't know. All right, let's stop there and scratch our heads, I guess. All right. No way. No, I think seeing problems is good once in a while. All right.